Hey, welcome to Math with Patrick. Today is Sunday, January 12th, and we will be solving the 12th problem from this Daily Epsilon calendar with Quill. He is back once again, and he's helping me out today with the math. All right, let's try it out. So we have a sum here, and the way that this notation works is that we're starting at the number 0, plugging it in to these x spots, and then incrementing or increasing it up to the number 1, and then plugging it in for these x spots again, and adding up all of these things all together until we reach this top number. Now, this top number is infinity, so this is an infinite sum. Let me write out the first few terms so I can show a bit better what I'm saying. So I'll start with x equals 0, and I'll just plug in a 0 wherever I see an x. And I'll do this for the first few terms. So there's the first one, and then I'll add when I plug in a 1. And then I'll increment my x to a 2, and I'll add the next term when I plug in x equals 2. And then I'll do one more term just to kind of like show the pattern, but eventually there's going to be an infinite number of terms, so it doesn't really make sense to write them all out. Instead, I'll just write the next one and put that ... at the end. This just kind of shows that it follows this pattern and it goes on infinitely. I'm going to simplify my fractions a little bit just so I can see what these numbers are. Up here, I have 2 times 0 plus 1, so that's 1. Then I kind of know from looking at this that it grows by plus 2 each time, so all my numerators are going to be odd numbers growing by plus 2. And just to make sure that my assumption of the pattern makes sense, I can see that 6 plus 1 is 7. And then for the denominators, I get successively bigger powers of 2. 2 to the negative 1 is a half, 2 to the 0 is 1, and then the pattern down here is that it's just multiplying by 2 each time. So the next term would be 9 over 8, I think, because I'm doubling the bottom and I'm adding 2 to the top. And I just don't kind of like how this looks, this 1 over 1/2. So I'll call that a 2, because 1 divided by a half is a 2. Okay, so here's my sum. I guess I could simplify this and call it a 3, because 3 divided by 1 is still 3. But just kind of looking at the terms, this doesn't yet help me know why the answer is going to be 12 just yet. One common strategy for adding series is if they're geometric, then there's like a formula for it. A geometric series is one where you have a common ratio and you multiply to get the next number in your series. But I noticed that like if I went from 2 to 3, I'd have to multiply by 1.5. But if I go from 3 to 5 halves, that's not another 1.5. Because like 3 times 1.5 is 4.5. And I know that this is 2.5. So I can't find a common ratio or a number to multiply to get to my next term. And so this isn't a geometric series. And so unfortunately, there isn't like a convenient formula for it out there. Instead, my plan is to try something with limits, actually. I want to see if I can rewrite the sum from 0 to this big capital N, and I'll see if I can take a limit as n goes to infinity. Now, it looks kind of the same as what I have up here with just 0 and infinity on the top, but my goal is to somehow rewrite this sum so that I can get some kind of function just in terms of n. And to be honest, I don't know how to get that formula myself. So I just asked an online calculator, and apparently the partial sum, as in the sum that goes up to some value of n on the top instead of infinity, is this. And so the calculator just said this was true. I don't actually know how to generate these on my own. However, I do want to convince myself that it's true, as in prove that this partial sum formula does work before I actually trust it and use it. So that's why I have this little question mark here. And mathematical induction is going to be my tool to prove that the formula here is the same as this partial sum. Induction works by first proving some base case, and that's going to be some kind of like beginning step. Essentially, that's going to be when n is equal to 0. That's the very, very first lowest number that I want to prove to be true for this formula. And after proving the base case, I need to prove something called the inductive step. That's where I'm going to assume that some step is true. And based on that assumption, I want to show that the next step is true. And the reason why these two things are enough, the base case and the inductive step, is that once I have the base case, I can start somewhere. And once I have the inductive step, that helps me go one step further. That would essentially prove that the n equals 1 case is now true. But then I can use that inductive step again. If I know that one step means that the next one is true, then I know that n equals 2 is going to work for this formula. And then so on and so forth. I could keep using this inductive step over and over and over again. Eventually, I will prove that this formula works for this partial sum for any value of n, as long as it's just above 0. And when n is equal to 0, this notation reads as plug in a 0 into this, evaluate it, and stop, because I don't have another term. I'm starting at 0 and I'm ending at 0. So 2 times 0 plus 1 on top, 2 to the power of 0 minus 1. And this is just the first term from our series from before. It's going to be this one right here. So I'm not going to write out the 1 over 1/2. I already did the math earlier. This is just a 2. And I'm trying to show that it's the same as this formula that I got from an online calculator. And I will plug in n equals 0 here and here. I get 12 minus this whole fraction. Looks like 2 times 0 plus 5 is just 5 on top. And then I have 2 to the power of negative 1 again on bottom, and that is a half. So that's equal to 12 minus 10. That is equal to 2, and I have proven the base case. Now it's time for the inductive step. So I'm going to assume that a certain step is true, and based on that assumption, I want to show that the next one is true. The only difference in notation between the assumption step and that showing step is that this k is incremented up by 1 in all the spots where you see a k. On the left side of this equation, I have a sum that goes from 0 to k plus 1. So I'm going to split this up into a sum that just stops at k. That way I can relate it back to my base case. So here is the sum that goes up to k, and then my next term will be the k plus 1th term. So that would be inputting k plus 1 anywhere I see an x. And in the bottom, in the denominator here, k plus 1 minus 1 is just going to be k, like that. I know from my assumption step that this sum right here is going to be all of this stuff there. So I'll do some substitution and replace the sum from 0 to k with 12 minus 2k plus 5 over 2 to the k minus 1. And this part, this k plus 1th term, is still going to be there, so I'll write it out. And ultimately, again, my goal is to show that this stuff down here is the same as this up here. I'm going to clean up the one up top just a little bit, so it'll be easier to compare what I get at the bottom here. I'm going to distribute this numerator. I get a 2k plus 2 plus 5, so plus 7. And then the k plus 1 minus 1 in this exponent is just 2 to the k. Now we just need to show that these two fractions combine to that one. So let's get a common denominator going so that I can add them. If I multiply 2 to the top and 2 to the bottom, I'll get a common denominator. So that 12 is still there. I'll multiply a 2 here. And then if I tack on another 2 multiplied to all of these 2's already there, that's going to just bring one more 2, and I can express that with the exponent. So then I'll add what's already there on the right side. And now that their denominators are the same, I can start adding, well, I guess subtracting the stuff in the numerators. Let me distribute this. This is 4k plus 10 on the left. So 4k plus 10. And then distributing and then adding this one over here, I get 2k plus 3. Here's 2k plus 3. And finally, I'll keep the 12 here. I see a minus 4k plus 2k. So that's like minus 2k. And then I see a minus 10 and a plus 3. So here I have a minus 7. And combining the denominators, I still have 2k on the bottom. So adding, or I guess subtracting these two fractions together, I get this one. And scrolling up, it's exactly what I had earlier. So I have proven by induction that this formula that I got from an online calculator does work, and it will work for any value of n that I plug in. Now, thanks to mathematical induction, I know that I can compare this infinite sum here on the left and this limit on the right. This formula is what I just proved with mathematical induction. Now, I just need to figure out what's the limit of this value as n gets really, really big. Well, at least this 12, this first part, isn't really going to change at all, no matter what value n takes. So I'm going to think about this 12 as just kind of being alone on the outside, and then I'm going to subtract the limit as n approaches infinity of that fraction. If I try it with direct substitution right now, if I plug in an infinity for both of these n's, I'm going to get an infinity over infinity, as in this top part grows as n grows, as does this bottom one. So I don't really yet know my limit. It still kind of looks like an infinity over infinity. And I'm going to use a limit concept called L'Hopital's rule. And this one allows me to reevaluate limits that have those infinity over infinity indeterminate forms. The rule is that I could take the derivative of the top and the derivative of the bottom and then try again. So I will try again here. I'm writing the limit as n approaches infinity. The derivative of the top is just going to be that slope. That's just a 2. And then the derivative of the bottom, that is an exponential function if you think of n as your input variable. And the formula for those is, let's see, natural log of the base times all this part as is. And I guess there's technically some chain rule going on in here because I do have an inside function, but the derivative of n minus 1 is just 1. So no big deal there. This 12 is still kind of hanging along for the ride. Okay, well, I'll try again with direct substitution. I'll see if I can plug in an infinity there. And I notice that I have a 2 on top and a number that grows massively big on bottom. And in limit world, if we have 2 divided by an infinity, that's essentially 0. It's 2 divided by a massive number, and that value is going to go right down to 0 as n grows larger. So I can evaluate this limit as a 0, and ultimately I just get this 12 right here. Wow, so in summary, we first inspected the sum and just kind of wrote out a few terms, though didn't really find anything there. Then I got this formula from an online calculator, and so something that I'm still wondering is how would I generate this formula on my own? If anyone happens to know, please feel free to leave a comment. That's still something that I'm not sure about. How would you create this partial sum formula for this sum? I don't know. But I do know that I can use induction to prove it. So I had a base case, then I proved that inductive step where I can always find the next step is true. And then finally, after confirming this formula and using some limits and L'Hopital's rule, I was able to say confidently that the sum, this infinite series, does end up at 12. Wow. Well, that's it for today. Thanks for coming along on this journey, and I'll see you tomorrow. Say bye.